Okay, we will continue with force acting on a current carrying conductor. Can you see me? Can you hear?
Can, sir.
Okay, thank you. Okay, before I start, for this smart tuition, I'll start online. Okay, because we don't know the SOPs for the MCO. So maybe we have to set 1 meter from one student to another student. Okay, so in this case, we cannot fit a big number of students in the tuition center. So we have to wait. So for this month, I will continue my tuition in online. Yeah. Okay. See some of you joining. Okay. Force acting on a current carrying conductor in magnetic field. Check the sounds there. Okay, force acting on a current carrying conductor in a magnetic field. So last week, what I give you is I give you a conductor which is placed in the magnetic field and it experiences force, and that force we can determine using Fleming's left-hand rule. Okay, Fleming's left-hand rule. So what I told you, your thumb, your thumb will represent force F. Okay, your thumb will represent force. Wait, so I'm asking to join. Okay, your thumb represents force, and then current, longest finger, we give I, current, and then the pointer over here represents what? Magnetic field. Magnetic field, we write the FBI. Remember the flow. FBI. Okay, FBI. So force, magnetic field, and also current. Okay, force, magnetic field, and current. Okay, so that I want to teach you the same diagram. Now I give you a slightly different diagram. Now only asking to join, a bit late. Okay, I will give you a bit different diagram. Okay, let's say here I place C-shaped iron here. Oh, wait. Okay, it's a magnet. Okay, so we attach a 2 bar magnets. Okay, 2 bar magnets facing each other. Okay, facing each other. And here is, let's say, it is North Pole. Okay, over here is a North Pole, and over here it is South Pole, facing each other. And then in between these magnets, I'm going to hang a conductor. So let's say here is a conductor. Okay, let's say I hang a conductor. And then let the current to flow through it. Okay. So there's a conductor is hanging like this, hanging. Right? It is hanging. Okay. In between there's a conductor hanging. So what is going to happen is it is going to swing. It is going to swing. So first I give you the direction of current. Okay, the direction of current. Let's say here, current flowing from here. I mean over here we connect to a battery. Yeah, battery. Up there's a battery, and then this conductor is hanging. Yeah, hanging. So now, first of all, what we need to do is we need to check the direction of the current flow. Where is the current flow? In this conductor. So current flowing, okay, from here inward. Okay, this is the direction of current. So we write I. First we write I, current. Okay, you want to sketch? Okay, can see, I think. Yeah, can see. Sketch first. Okay, this is the direction of the current. Okay, so now current flowing from where is it? From here, it is flowing inward. Yeah, it is flowing inward. Okay, inward. Okay, now let's check the direction of the force acting. If you use the Fleming's second rule, where is the current? Current is in here. Let's say I'm observing this diagram from here. Okay, look at this diagram from. Wait. You have to update your Zoom app, yeah? Okay, so what happens is there will be force acting and will make this conductor to move to a side. Okay, let's check using the Fleming's second rule. Where is the current flow? Currents are inward. Okay, current is in. Okay, your third finger over here. Please point inward. In. Follow it. Inward. You can see clearly. And then I told you, right? The second finger pointer. Please direct to the south. Turn. Turn to the south. And then where you can see your thumb points. Your thumb points to the right. To the right, yeah? Your thumb points to the right. I repeat, current is inward. So the third finger over here must be directed inward. Inward. And then north to south. So you can see your thumb is what? To the right. To the right. So what happens is this conductor will be pushed to the right. So the force will be acting to the right. So we label with a F, force. So this conductor will swing. Okay, this conductor will swing. Let's say until here. It is swing. Okay, it will swing. Okay, yeah. So now why it swing to the right? Because of there's a force acting. Can you explain how this force can be exerted on this conductor? Okay, what we have to do? We have to draw the catapult field. Yeah? So let's check using catapult. Catapult field, or we say medan elastic. Yeah, medan elastic catapult field. Okay, so we check over here is what? North pole, over here is south. So first we check over here. Okay, verb it is. We assume that you're observing from here. Yeah? From here, you're observing from here. This side. Okay, so here south. Over here is north. And then if you're observing from this side, from here, current is what? Flowing inward, yeah? Inward. So we have to put dot or cross. I told you, right? If inward, okay, let's say there's an arrow, right? It goes in, you're looking at the back. So we need to put a cross, yeah? Cross. So here, current is flowing inward. Okay. This is a catapult field that you need to know how to draw. Okay, let's check using Fleming's standard rule. Where is the current flow? Current flow inward. Okay, let's check. Fleming's standard rule. Current is in. In, please apply the rules, then only you can understand. Okay? In, and then north to south. Where your thumb points? I repeat again. Current is in. Okay, the third finger. Current I, longest I. Okay, so current is in. North to south. Your thumb points to the right. Correct? Okay, always the second finger over here must be fired towards the south. They don't say fire in the exam. Okay, so must be directed towards the south. I mean, it will represent a magnetic field. Okay, so where is your thumb? Your thumb is to the right. So the force will be acting to the right. So we draw arrow and then right F. So if the force is acting to the right, how about the magnetic field? So you will see what? More magnetic fields on the left hand side. So this one you must practice to draw. So in the exam, please draw more magnetic fields on the left hand side. So it will be like this. Always start from north, but don't take exactly center. We know the force acting to the right. So we start on the left hand side and pull the line to the left. Sorry, we start from the right hand side, from the north pole. We pull the line, then take the curve part, go to the south. Then we do it again, more fields. Must practice. And then on the right hand side, we draw only one, less. So less concentration of magnetic fields. Yeah, very few magnetic field lines. Please change your name in the chat, in the participants column. I can see over here some funny names. Please change. Okay. So this is what I call catapult field. So if you know how to draw this, we can give you up to 3 marks. 3 marks. So this is what I call catapult field. But anyway, you will lose 1 mark because of there is no magnetic field. Okay, the direction of the magnetic field. So the direction must be from north to south. Wait, So this is what we call catapult field. Okay, I'm going to give you 2 more diagrams. I want you to draw the catapult field. Yeah? But before that, use the correct rules. Identify the force acting. Yeah. Okay. So now I want you to draw the catapult field for this. Later I will teach you one more. One more. Okay. Okay, draw the catapult field for this line, this diagram. Can you see it? Can you see it?
Sir, dot or cross, sir? Dot.
Oh, it's not clear. You know, I change place. Okay, I draw over here. It is dot. Okay, it is dot. Okay, it is dot, and then one more. Okay, draw the catapult field for these 3. Okay, one done ready. Number 2 and number 3. I want you to draw the catapult field. Draw. Use correct rules. Fleming's left-hand rule. Then identify the force. Okay. Draw the direction of force. Then only the resultant magnetic field. Finish? Okay. 30 seconds more.
Okay, done.
Maybe some of them still drawing. Wait for a while. Give them time. Okay. So I think we can check. Later we teach you one more rules. One more rules. Okay. Now, here, where is the current? Current is out. So the third finger over here must be directed outward. Okay, out. Okay, as you can see, I'm using two computers over here. So let's double check what I'm displaying. Can you see or not? Okay. So current is outward. The third finger over here must be pointing towards you. Okay. Then magnetic field. So what I told you is a B. B. Here is force. Over here is current. Okay. So current outward, outward, north to south, north to south. Your thumb points upward. So your thumb points what? Upward. So the force acting upward. Okay. So is the force acting upward? How about the resultant magnetic field? So you will see what? More magnetic fields below. So start from north. Don't think exactly the center. Okay. You look at the four figures over here. Goes down. More fields will be below. Okay. So we start slightly higher. Goes first and come up. Upward. Yeah? Then draw more lines like this. And don't forget to draw the direction of the magnetic field from north to south. So there must be direction. Okay. Now we come to the third one. Where is the current? Okay, current is outward. Dot. Still dot. Okay, still dot. Okay. Current is out. Out. Okay, current is out. Current is out. And then magnetic fields to the south. Okay, correct? Okay, current is outward. Magnetic field to the south. Your thumb points where? Your thumb points to the right. Sorry, to the left, yeah? To the left. So we draw the force that acting to the left and label with the F. And then how about the fields? So we start from the north. Let the magnetic field goes to the right hand side, yeah? Okay, so it will be like this. And arrow, don't miss the arrow. Okay. So here what rules we are using? We are using Fleming's left hand rule. Okay, Fleming's left hand rule. So spelling must be correct. So there's another rule that we can replace the Fleming's Latin rule is we also can use right and slap rule. Okay, right and slap rule. Okay, let me teach you the right and slap rule. Okay, your right hand. Are you ready? Okay, your right hand. Okay, right hand slap rule. Okay, let's check over here. Your thumb. Yeah, your thumb over here. Okay, remember. Here we are using Fleming's Latin rule. Come to subtopic number 3, induction. Over there we are using Fleming's right hand rule. Got difference. So you have to differentiate these two. Okay. Here for the Fleming's Latin rule, we are using replacement right hand slap rule. Okay, right hand slap rule. Okay. But when we come to the Fleming's right hand rule, we cannot say, oh, replacement, there's another rule. Oh, left hand slap rule. No. No left hand slap rule. Wrong, eh? Okay. So, right hand slap rule, your thumb will show the direction of the current. And then the 4 fingers over here will show the direction of the magnetic field. So let's check. Where is the current? Current in. Current in, your thumb. Okay, your thumb, right? Your thumb must be pointing inward. Because from here, when you're observing, it is what? Inward. Okay, current is in. Okay, your thumb must be inward. And then, wait. Okay, your current is inward. Okay, then to the south. Point these fingers to the south. To the south. Then slap. Slap. Where it goes? Let's say if I place this conductor over here, current is in to the south. If I slap, what happens? It will push to the right. So it will move to the right. Force acting to the right. Okay? So come to here, let's check. Let's check. Current is in. Current is in. North to south. Then slap. It will move to the right. Simple. Okay? It will move to the right. Wait. So I'm Shiva from USGKL. So after I press link, cannot join. Wait, off your mic, please. Wait, here was problem with this student. Join without you. Tian. Okay. So first that, okay, now we go for the second one. Right is left rule. Where is the current? Wait, this student. What happened? Zoom. Your meeting should start in a few seconds. Wait. Wait, click join. Okay. So for the second one, where is the current? Current outward, yeah? Current outward. So the thumb must be outward. Outward. Then the four fingers over here, direct to the south. So I repeat, current outward, magnetic field to the south. Then if you select, where? It will be upward. Yeah? Okay, current outward to the south. If you select, where it goes? It goes upward. Okay, clear. Okay, this one clear. Now we go for the number 3. Okay, number 3, current where? Also what? Outward. Okay, current is what? Outward. Then current dot is what? Wait. Wait, I click join, but ready, same appears. Wait, permitting to stop. Please shut down. Shut down. And come back. Okay. Okay. So current outward, and then the fingers over here must be directed to the south, yeah? To the south. Current outward to the south, then set. If you move to the left. Okay, it will move to the left. So finish. Simple. Right hand, flat rule. Okay. So now let's go for the next one. Is an experiment. Yeah? Experiment. Okay, experiment. Okay. Now the force acting on this conductor. Okay, let's say you want this conductor to be what? Push to move further. Also can be asked in terms of comparison. Yeah, comparison. So let's see the current that flow over here is I. Yeah? Current flow is what I. But the second one over here, the current flow is what I. Bigger current. Okay, current over here is increase. So when the current increase, okay, when the current increase, okay, when the current increase, what happens to the angle where it swing? Angle where it swing increase. Why? Why the angle where it swinging increase? Because of what? Because the force acting is what increase. That's why it will be displaced more. So now the force acting on a current carrying conductor in a magnetic field depends on what? Okay, so we got an experiment. You want to screenshot this scan, then later you can redraw. Okay, screenshot, and then you can redraw later. Faster. Okay, finish. So now we check the next one is a force acting on a current carrying conductor depends on force acting on a current carrying conductor in magnetic field depends on force acting on a current carrying conductor in a magnetic field. In magnetic field depends on, so there will be three. Sorry, here only two. But the next one, the next one will be three. Okay. Number one is current. Okay, current I. Okay, number two is strength of magnet. Strength of magnet. So here, when you come to the experiment, how you are going to increase the strength of magnet? We can use what? Number of magnets. Okay, so when the magnets is become stronger, the magnetic field lines will be what? More magnetic field lines, so the force active what? Become greater. So now I'm going to discuss with you the experiment from here. So we need to go through these two details. Yeah, the last year experiment came out from chapter 2 electricity. Okay, this year maybe they switch to chapter 3, or maybe they will remain. They will go back to chapter wave. Yeah. Okay. As normal. Okay. The title experiment. We want to find relationship between current and magnitude of force acting. Okay, we want to find the relationship between current and the magnitude of force acting. Okay, as normal, A, B, C1. Leave two lines for each. Okay, leave two lines for each. Okay, we come to C2. Manipulated variable, corresponding variable, and constant variable. Okay, manipulated variable. But in the exam, please write complete. Yeah? Manipulated variable, corresponding variable, and constant variable. So manipulated variable is current I ampere. Responding variable, okay. Actually, the force. Never mind. You write this first. Later, I'll explain to you. Distance or displacement. We use this here. Displacement or distance better. Distance moved by copper rod. So we write any letters. Okay, can. So distance moved. Yeah. You can see here, distance moved by copper rod. Okay, distance moved by copper rod. D centimeter. You want to change to X centimeter, L centimeter also can. Okay, so distance. Later I tell you. Distance over here indicates the magnitude of force acting. And constant variable is number of magnets. Number of magnets or strength of magnet. Number of magnets or strength of magnet. So the next one is the materials and apparatus. Okay, list the materials apparatus. Leave it first, a small space. Okay, 2 lines. Later you can rewrite again from the diagram. Okay, so we go for the number 4, which is a bit difficult. So we need to learn the correct method of drawing. If you look at the whole diagram, yes, it's a bit confusing. Yeah. So let's just learn. Yeah. This one I think they ask only once in SPM. Only once. Once or twice. I think they ask twice in SPM. Twice, yeah? So for chances to ask again, so better be careful. So first of all, we need to draw the same diagram like this. Okay? So we need more space on the right hand side. Okay, C-shape iron rod. Okay, C-shape. But this one I don't want to add it. I don't want to add this one. They were disturbing. So the one. I remove this line. And then let's say here is North Pole, over here is South Pole. Okay, here North, over here is South. Okay, here North, over here South. And in between these two magnets, okay, in between these two magnets, we are going to place 2 thick copper wire or aluminium also can. Aluminium rock also can, but must be thick. Yeah. So we place 2 thick copper wire. Okay, we place 2 thick copper wire or copper rod. Okay, it must be straight. And then over here we draw. Okay, you start to draw this first. On the right side, later I will show you how to draw the balance, the electric circle. Yeah? So start to draw the magnet first. Must know to draw, the diagram may be difficult. Okay, done. Once finished, tell me. Yeah?
Done, sir.
Done. Okay, good. So here we place wooden block. Yeah? Wooden block. Okay, here we place wooden block. Okay, there's a wooden block over here. And then the copper wire or thick copper wire, what we need to do is that we have to use the thumbtack or silicone tape. Okay, we have to paste over here, or you put thumbtack or paste. Okay, you have to paste or put the thumbtack so that these two thick copper wire can stand straight. Okay, on the right hand side, now we are going to connect to the rheostat battery. Okay, and also ammeter. The important one is the rheostat, battery, and ammeter. Okay, before that, you go to the chat box. Please type your name and also the name of tuition center. Type your name and also the name of tuition center. Okay, after that, you come to the right side here, we have to draw the circuit diagram. Yeah? Circuit diagram. So after this is simple. First, here is the most important. After this, just draw a circuit diagram which involve the symbols only. Okay. Okay, here I fix. Okay, I draw a rheostat. Then here I put an ammeter. Battery. Make it simple. Yeah, make it simple. Okay. Finished. Later we will label this. Yeah, we will label this. Important is the C shape, and then the two thick copper wires stand straight, and then on these two thick copper wire, we are going to place another rod, yeah, like this. Very light rod is going to be placed on these two thick copper wire, but only copper wire, no insulator, yeah, no insulator. So we place a copper wire over here, a copper rod. Okay, it is a copper rod. Yeah, this copper rod will be pushed to a side. Okay, it will move to a side. Okay. I'm searching for the video clip where I don't know, let me see. Okay, now let's label here. You have to label it, you have to label everything. Magnet, you can label. Okay. This one we label as thick. Okay. This one we have to label with bare thick copper wire or thick bare copper wire. Okay. Thick bare copper wire. B-A-R-E. Thick bare copper wire. What is meant by bare copper wire? Some sort is it naked? Naked is what? You remove. There's no insulator. Okay, we remove only the copper wire. But must be thick. Why? Because we want this copper wire to stand up straight. Yeah, to stand straight. Thick bare copper wire. Okay, thick bare copper wire, and then here you write wooden block. The rest I think no problem. Battery, or you can write DC power supply, emitter, rheostat. But in the list of materials apparatus, don't forget to write connecting wires. Yeah? Connecting wires, magnet. The name I think is no problem for you. Okay. The next one is this. Okay. C-shaped iron. Yeah. Okay. C-shaped iron yoke. Teras besi berbentuk C. PUBM. C-shaped iron yoke. Okay. And then here is what? Copper rod. Okay. This one represents copper rod. Okay. Wait. I write below. Okay. This one represents copper rod. I think they won't teach this in school, but it's important for physics. Experiment important. 12 marks will be given. Okay, copper rod. Okay, now complete. The rest magnet you can write on your own. Magnet, rheostat, emitter, battery or DC power supply. Battery or DC power supply. And don't forget to write connecting wires. Okay, finish. Okay, now first we check the. Actually, I did draw the diagram over here so that the conductor will move to the right. Yeah. Okay. Now let's check. First of all, you see over here positive terminal. Positive, negative. Current flow, where is it? Current flow from here, where is it? On this conductor, it will be flowing inward. Yeah. So this is a direction of the current flow. Okay. I draw the arrow and then write I. Direction of the current I. And then now what happens? This conductor will be moving in this direction. Please check using Fleming's rule or right hand step rule. Here, tell me in this direction this conductor will move. Please check. Please tell me the direction where this conductor will move. Answer?
Move to the right.
Move to the, yes,
Right.
okay, let's check. Current is in, from here in, not to south. Your thumb points where? To the right. To the right. So this conductor will move to the right. It's slightly curved here. So what we need to do is we need to measure the distance over here. How far is moved? I mean, we need to measure the distance. If let's say if you supply more current, increase the current, what happens? This conductor was acting to the right. Okay, so this conductor will move further. Okay, so we need to measure the distance, move, and then the force acting is to the right. Okay, we write F, force acting to the right. So let's say if the current is increased, what happens? This conductor will move further. It will move somewhat further. So the distance over here indicates what? Indicates the magnitude of the force acting. So the further the distance move means what? Greater the force acting. So maybe in the exam they can give you two diagrams with this. One with a small current, one was what? Bigger with a larger value of current, and then they ask you to compare current, they ask you to compare the distance move. I repeat, they can give you two diagrams. Diagram, for example, 10.1 and one 10.2. Current, let's say over here 0.5, and then distance move. And then one more, 0.6 or 0.8, distance move is further. So they can ask you to compare the current, they can ask you to compare the distance move, they can ask you to relate the distance with the force. Okay, they can ask you to relate current and the magnitude of the force acting. It's very simple, easy to answer in terms of comparison. Okay, so further the distance it moves, it shows what? Greater the force acting. But here we are not measuring force, we are measuring distance moved. Okay, distance moved by the rod. Okay, we are measuring the distance moved by the rod. Okay, now for the number 5, we will procedure. Okay, for the procedure, you leave about 6 to 7 lines. 6 to 7 lines, leave it. Okay, we go for the number 6. This one 5. Number 6 will be tabulation of data. I ampere, and then here is D centimeter. Okay, then here currents, we write 5 values. So 0.2, 0.2, 0.4, 0.6, 0.8, 1.0. Okay, 0.2, 0.4, 0.6, 0.8, and 1.0. And then the last one is number 7, is how you're going to analyze the data. So just a graph only. So not enough space on this board. So I will write a bit smaller. Okay. Y-axis is a responding variable. X-axis is manipulated variable. Those just joining here, please go to the chat box, write your name, type your name. Okay, done. Now I'm going to teach you the balance here, the balance. Already type your name. Re-enter this now and type your name, but press now I will return like this. Once you type your name, no need to retype again. Huh? If let's say you exit group join, sure you cannot see all the settings, right? So no need to type again. Okay, finish. So number 5 is a procedure. So you do about 6 to 7 lines. Okay, now you write the answer for the A, B, and SOC1. So for the remember here for the report writing without data, you write the answer based on the experiment. Okay, no problem. Normally some school teacher they ask A, no, must based on the situation. Okay. So for example, if you are using blender or if you are using fan, you want to increase the speed of the fan. What you do? You just increase, turn the knob or press 1, 2, 3 or 5. Okay. What happens? The fan will rotate faster. Means what? You are supplying more current. More the current is supplied, it will rotate faster. Okay. So, okay, for the A, distance moved by copper rod depends on current. Or you can write this. Force acting on a current carrying conductor, force acting okay, right there. Force acting on a current carrying conductor, force acting on a current carrying conductor depends on magnitude of current. Depends on magnitude of current. Force acting on a current carrying conductor depends on magnitude of current. Or you know what? You can write this. Distance moved by copper rod depends on current. Okay, distance moved by copper rod depends on current. Okay, distance moved by copper rod depends on current. Okay, can also. For the inference, hypothesis, and aim, all the answers to the set. Okay, for the B. For B, you write when current increase, this one B must based on the experiment, yeah? When current increase, distance moved by copper rod also increase. When current increase, distance moved by copper rod also increase. Okay, when current increase, distance moved by copper rod also increase. Okay, when current increase, distance moved by copper rod also increase. Distance moved by copper rod also increase. Okay, for the C1, To investigate the relationship between current and distance moved by copper rod. To investigate the relationship between current and distance moved by copper rod. To investigate the relationship between current and distance moved by copper rod. Okay, to investigate the relationship between current and distance moved by copper rod. So almost done, but the procedure is missing. But remember, if you didn't write the procedure, the rest marks gone, yeah? But you can write the procedure based on this. Okay, so what you're going to write? First one, 1, 2, 3, 4, 5 values must be written in the procedure, but the first one is here. Okay, mandatory variable, the first value you must tell, and then second is what? You must tell how you're going to measure and record the responding variable. Okay, listen first. First, yeah, what you need to do is you need to arrange the material separators as shown in the figure. Then you have to adjust the rheostat. Okay, adjust the rheostat until current flow becomes what? 0.2 ampere. Okay, current flow becomes 0.2 ampere. Wait, later I tell you. Then, okay, then what you need to do is off the circuit. Place the two magnets as shown in the figure. Okay, after that, you on. You cannot place the magnet and then conductor adjust the rheostat. Cannot, because the conductor will keep on moving. So what you need to do is what? You need to adjust the rheostat, adjust the current until 0.2 ampere. Then off the circuit. Switch off the circuit. After that, only you place the two magnets, switch on. Then the conductor will push. You move to a certain distance. Then you measure distance. So the distance over here indicates what the magnitude of the force acting. Okay. So please, I tell you. Please write procedures. Okay, for the procedure. Adjust rheostat. Adjust rheostat until current flow in the circuit become 0.2 ampere. Until current flow become 0.2 ampere. Adjust rheostat until current flow in the circuit becomes 0.2 ampere. Okay, current flow becomes 0.2 ampere. Okay. Next step, switch off the circuit. Next one, switch off the circuit. Okay, switch off the circuit. Then third, you write here third. Place the two magnets as shown in the figure. Place the two magnets as shown in the figure. Okay, place the magnets as shown in the figure. Finish. Next step. Switch on the circuit. Next point. Switch on the circuit. Switch on the circuit. Go stop. Continue. Continue. Measure and record distance moved by copper rod using ruler. Switch on circuit. Full stop. Measure and record. Measure and record distance moved by copper rod using ruler. Measure and record distance moved by copper rod using ruler. Okay, measure and record distance moved by copper rod using ruler. Okay, finish. The third one. Third one is, sorry, the last one is what? Repetition. Repeat the procedure above. Repeat the procedure above. Repeat the procedure above. Using currents of 0.4 ampere, 0.6 ampere, 0.8 ampere, and 1.0 ampere. Repeat the procedure above using currents of 0.2 ampere, 0.4 ampere, 0.6 ampere, 0.8 ampere, and 1.0 ampere. Okay, done? Okay. Finish it? Okay, now the second one, just remember this now. No need to write again. If you're writing, then do experiment for 1 day. It's not enough. Yeah, sorry, it's not the right way. So you must know how to switch. Okay, now how about the strength of magnet or number of magnets? If let's say we are using a strong magnet, okay, how to increase the strength of magnet? If you got if you measure the strength, okay, no problem, but we cannot measure strength. Yeah, so what we're going to do is what? We are going to increase the number of magnets. Okay, don't copy this. Just listen. We want to find the relationship between number of magnets and the magnitude of force acting. Okay, magnitude of force acting. So this one I remove. Okay, current, number of magnets also I remove. Okay. Current here is number of magnets. Number of magnets. Okay. So the diagram still same. Diagram still same. So here we write number of magnets and units 1, 2, 3, 4, 5. Okay, here current we remove and then we write N units. Okay. Hold on. Okay. So, you can screenshot this. Okay. But ABC1 you can use variables. Matrix operators no problem. Only the procedure will be changed like later I tell you. Okay. So for the A, how you will write? You write this straight away. Distance moved by copper rod depends on number of magnets. So that means this here. Let's say if I add one more magnet, that's now only one, right? But now it's what? Two magnets. So when we are using more magnets means what? In between it will produce a stronger magnetic field. If the magnetic field is stronger, what happens? The force echoes are stronger. So you don't need to draw more magnets like this, not one enough. And you must understand the idea. So when you add more and more magnets like this means the magnetic field getting what? Stronger, the force acting become greater. Okay? So for the A, distance moved by copper rod depends on number of magnets. B, when number of magnets increase, distance moved by copper rod also increase. B. C1, to investigate the relationship between number of magnets and distance moved by copper rod. To investigate the relationship between number of magnets and distance moved by copper rod. Switch the variable only. Okay. Matrix operators stay same as just now. No change. Normally, students really worried about the report writing, 12 marks, really worried. You know, why? Why they worried? Because of they didn't study the experiments in school. Okay, but I'm teaching you over here with a very detailed explanation, although you're not conducting this experiment. Yeah, at least you got the idea. So easy for writing report and also easy to answer the structured questions or essay question. We come to comparison, yeah, in terms of comparison. Okay. And then for the procedure, what you need to tell is, okay, same as now, no need to copy. Just listen. Switch on the circuit. Adjust rheostat until current flow become 0.5 ampere. 0.5 ampere. Okay. Then switch off the circuit. Place one pair of magnet in between the copper rod as shown in the figure above. Okay. Switch on the circuit. Measure and record distance moved by copper rod using ruler. Repeat the procedure using two magnets, 3 magnets, 4 magnets, and 5 magnets. Okay, finish. Then only come to table and also graph. Understand or not? Understand or not?
Yes, sir.
Got it here? Okay. So no need to write 2 reports, just only one, just switching the variable. Simple. Never mind, I will give you all these reports again. I will give you again. Like what I gave you last year, Form 4, right? So this year I will give you again for the Form 5. Yeah? Once I finish this chapter, I will give you the list of experiments. Okay, finish? Finish here? So now let's continue. Still subtopic 2. You can screenshot this experiment. You can screenshot if you want. Finish? Okay. Now we are going to go through turning effect on a current carrying conductor. Okay, let's see. Here is a fan. Okay, there is a brakes. There's the knobs over here, right? Knobs, huh? Okay. Oh, very nice, my drawing. Okay, now if you on the fan, what happens is spin, right? Is spin. Okay, let's say here 0. Okay, 0 off here. 1, 2, or let's say one more. 3. We can increase the speed by pressing the number that you want. 1, 2, 3. So the 3 days of the fan will rotate faster. So now, how the fan can rotate? How it can rotate? Okay, so that's one that we are going to go through. So now we are going to go through turning effect. Turning effect on a also got experiment, but I'm not going to this because we discussed this. This is the one. Okay. Okay. Turning effect on a current carrying coil in magnetic field. Okay, turning effect on a current carrying coil in magnetic field. Turning effect on current carrying coil in magnetic field. Okay.
Sir, your camera blur.
Okay. Here I already draw two magnets where these two magnets facing each other. Okay, they are facing each other. That means in between got magnetic field. But now I'm going to place a coil in between. A coil, yeah? Okay. So let's say the coil is like this. Okay, never mind. See how I'm going to draw it. See how I'm drawing this. Okay. You can see. Okay, it is a flat circular coil. Okay, flat circular coil, and here we cannot see, right? So I make it dot lines. Yeah, I make it dot lines because we cannot see this side. Okay, and here got some more components. Later we will check it later. Okay, not now. Finish.
Finish, sir.
Okay. But now in this coil, flat circular coil, there's no current flow. Let's say there's a current flow. Current flow. Okay. Current flow. Start over here. Current flow. So here on this coil, where is the current flow? Where is the current flow? Okay. Let's say if I label over here as A, B, C, D. Here, A, B, C, D. On the side AB, the side AB, where is the current flow? Current flowing from A to B. Okay, we draw the current over here first. Current flowing A to B. Current flow. I. Okay, this one we check later. We get the idea first. How the turning effect reduce on this coil. Okay, current flow A to B. BC, don't worry because there's no force acting on the side BC. Later I tell you. But come to CD, where is it current flow? Current flow from A to B, B to C, and C to D. C to D. Okay. So we already draw the current. Okay. Next we use the Fleming's Latin rule. Identify the direction of force acting on the arm AB and also arm CD. You mean the side. Okay, let's check over here. This side. On this side. Okay, at this side, the force acting over there. On arm AB. Okay, please check using Fleming's Latin rule. Left hand, current is in. You're observing this diagram from here, from the front, yeah? From the front, here. Okay, current where? Okay, on the left hand side is in. So we place in. Not to south. Not to south. Where is the thumb? Points downward. I repeat. Actually this one I have to teach in tuition center. But now maybe you got chances to confuse, so I go a bit slow. Eh? Because not all the students can get ID easily. Eh? Okay, now here current where? In, north to south. Your thumb points downward. So the force acting over here, it is downward. Okay, label with F. Label with F. Okay, on the right hand side, where is the force acting?
Upward.
Upward. Yes, sir. Okay, let's check. Where is the current? Current is towards us.
Come
Towards.
out.
If you're observing from here, okay, towards. Not to south, to the right. Okay, to the south. Always fire to south, yeah? So your thumb points upward. I repeat, current over here C to D, if you're observing from here, is what? Upward. North to south, your thumb points upward. So here, the force acting is upward. So we label with the arrow over here and write F. So where is the force acting? On the right side is upward. So let's say if you are in the car, there's a steering, right? If you turn, so the car also will turn, correct? It will turn. So here, what happens is the coil over here will rotate in anti-clockwise direction.
Sir,
It will rotate in anti-clockwise direction.
sir, the direction of force you can teach using the right hand slap rule. Just to check.
Okay, can. Not to say cannot, can. But I'm worried some school teachers, they want to accept.
Or not in syllabus.
Actually can. Actually can. In 2016, okay, came out this question exam. Answer is the Fleming's Latin rule. So when they discuss, they just give only one answer, Fleming's Latin rule. But luckily, I said, why not this rule cannot? Then only they're searching. Google. Yeah? Right hand slap rule. Then after check, they said, oh yeah, got. Then they add. So anyway, you can check your textbook. In the textbook, they mention about this. Replacement for the Fleming's Latin rule is right hand slap rule. Accepted. Okay, now we try to write the correct answer, best answer.
Okay.
Because I know in that year, normally my students will write right hand slap rule. Okay, luckily I was there, so I said, why not this one not accepted? So then towards the end, they accept the right hand slap. Yeah. Okay. So here it produces a turning effect. So the direction of force we determine using Fleming's Latin rule. So now the problem is how this turning effect is produced. So they ask this question exam. How? Can you explain? Can you explain how the turning effect is produced? So it's not easy. But we can see the answer in terms of diagram. So now for this question, the diagram will be the answer. Okay, the diagram will be the answer. So how? Okay, let me give you the idea first for this. Okay. Okay. Before that, if you look at here, north, over here it is south. So it is a flat magnet, yeah, flat magnet. And then if it is a flat magnet, what happens? The magnetic field lines will be what? It is not uniform. If uniform, all must be straight. All must be straight, but it's not uniform. But it is almost uniform. Center will be what? Center will be almost same. So we say almost uniform, but here is what? Curve outward. So later I tell you what is the correct shape of the magnet, which also can be the answer. Yeah, but this flat magnet is not suitable. Later I tell you. Okay. So magnetic field, and then in between got current. Okay, two conductors, AB and also CD. Okay. So on the left hand side, current is in. So current in, I put cross. Current is in, and then the magnetic fields clockwise or anti-clockwise. Clockwise, anti-clockwise. Current in. Curve the figures. Clockwise, anti-clockwise. Right hand side rule. It is
Clockwise.
clockwise direction. Okay. So it will be in the clockwise direction. Combination of topic 1, yeah? Clockwise direction. This one for the arm AB. AB. Okay, on the side AB. Okay, now come to CD. Where is the current? Current is what? So observing from here is outward. If outward, okay, on the right hand side, it is dot. It is a dot. Then magnetic fields. Clockwise, anti-clockwise. If dot current is out. Out.
Anti-clockwise.
Yes, anti-clockwise. Anti-clockwise. And this one for what? CD, yeah? CD. Okay, now you can see this coil, okay, left hand side, magnetic field surrounding the conductor is in the clockwise direction. On the right hand side, the magnetic field is what? In the anti-clockwise direction. But the problem is what? These two fields are in the magnetic field of the permanent magnet. Okay, in the magnetic field of the permanent magnet. So north, over here south, then left hand side it is cross in magnetic field is in the clockwise direction. I copy this diagram over there. Okay. And then on the right hand side is a dot. Dot. Magnetic field will be in the anti-clockwise direction. So what I did, I copied this and place it in between the magnetic field of the permanent magnet. And the permanent magnet, the magnetic field will be like this. Okay, it is from north to south. So now when these three magnetic fields combine, it will produce a couple. Couple, you know couple? That couple is different. In BM we say sepasang daya kupel, Kupel, kupel in BM. So namanya, so it will produce a pair of forces or couple of forces, or produce couple also can. Produce couple. Okay. So how about the resultant magnetic field that form? The next one is the correct answer. Okay, the next one is the most important. So the resultant magnetic field will be like this. North, south, left hand side current is in, right hand side current is out, is a dot. How about the resultant magnetic field? Okay, you draw this, later I teach you how to draw the magnetic field. Must know how to draw because it can give you 4 marks if you draw this, not this diagram. Okay, this diagram is the most important. Okay, finish. Okay. Okay. Now, look at this. Okay, here you can see three magnetic fields. The black, blue, and so on. Red. So we start with the black first. Black color magnetic field. Okay, the black color magnetic field. And then you can see the blue color magnetic field. So the black. The four fingers over here represents the magnetic field of the permanent magnet. And then here is the blue color. Okay, so these magnetic fields, when combined with the magnetic field of the magnetic with the conductor, so you can see over here is a curved part. Okay, it is what? Taking a curved part. So what happens? These magnetic fields will be pushed to go up. Okay, so this magnetic field combined with the blue color magnetic field, it will be pushed to go up. Come to the right hand side. Okay, come to the right hand side. You can see over here it is mixed red color magnetic field. What happens? It will be forced to go down. I repeat, the magnetic fields on the left hand side from the magnetic field, permanent magnet, it will be forced to go up. Then come to the right hand side, it will go down. And then so what happens? Here the magnetic field lines become more, here less. Here more, here less. So what happens? The force will be acting from the region of higher concentration of magnetic field to the region of lower concentration of magnetic fields. So, but before that, we draw the direction of the force first. Then easy for us to draw the magnetic fields. So where is the force acting? Where is the current? Current is in. Current is in. Okay. Check. North to south. Okay. Current is in. North to south. Your thumb points downward. So here force acting downward. Okay, how about the right hand side? Current is out. So the third finger over here must be upward. Magnetic field to the south. Where your thumb points? Upward. So the force acting over here is upward. And we label with F. So why there is these two forces acting? Because of the combination of magnetic field. Okay, the combination of magnetic field produces a couple or constitute a couple. So the result of magnetic fields. Okay, you must know how to draw. Wait first. You start from north. Here. Okay. Start from north, but don't be at the center. The one. So we start slightly lower. Okay. Then we go close to it for the first one. Close to it. Then come to the second one. Don't go closer. Why? Because if you go close, then we come to the second one. What happened? Rapid jam. Become very close already. So you will face problem in drawing. So don't make mistakes. The one. So we follow this method. Wait. First one, no problem. First one, no problem. Okay. But when it comes to second one, you go slightly further. Pull slightly downward. Then end at a lower level. Okay, and at lower level. Then come to the second one. Goes up slightly. Then third. This one must be closed. Okay, so we already draw more above over here, and here's some more. Then we draw only one goes above. Only one over here. To show the difference in the concentration of the magnetic fields. Okay. So, okay, after that, just for this, they give you 3 marks, but don't miss the direction of the magnetic field. You have to draw the direction of the magnetic field. Okay. Okay. So here you can see over here it produces what? Produce couple. Produce couple means a pair of forces. We say couple. Okay, the resultant magnetic field. Okay, the resultant magnetic field, I mean the combination of magnetic field for the permanent magnet and when you use it the coil, the conducting current, it will constitute a couple. I mean a pair of force where this pair of force produce a turning effect. Or you can write this. The turning effect produce a couple of forces. Okay. Turning effect couple of force. Okay, the turning effect produce couple of force. Okay, diagram. This one, they give 1 mark here. They asked this question before. 1 mark given for the direction of the current. 2nd mark for the pattern only. Here more, here less. 3rd part, 2nd mark. 3rd mark they give for the arrow, magnetic field lines. 4th mark, draw and label the direction of force. 4 marks. So they mean here important. Yeah, you must know how to draw.
So, sir, if exam they ask how the DC motor function, so we just draw the diagram for them lah.
DC motor function. No, the question is not complete. Yeah, the statement is not complete.
Turning
DC
effect.
motor,
I mean
check.
the turning effect. Explain the turning effect.
Yes. Explain how the turning effect produce. You draw this and label this down. But how the DC motor function, that one is different story. You need to explain detail, but they won't ask you so detail like that. No, they won't ask. But I will teach you detail so that you can get the idea what actual thing is going on. Okay? So if I clear that and come to the induction, we got 2, AC and also DC. That one we can finish out very fast. Once I finish this, after that, very fast. Yeah? Only the subtopic 2 and 3 will take time. Okay, so now, finish it. Okay, now we go for the shape of the magnet. Okay, if you look at here, the shape of the magnet is not suitable. Okay, the shape of the magnet is not suitable. So we have to choose the correct shape because this was what can be one of the question in the exam, and then you must know the reason. Okay, the shape of the magnet is not suitable, so we have to choose What is this? What is this? What is it? Circle, right? Hey, what is this?
A circle.
Huh? Circle. Okay. And what is this? What is all this?
Radius.
Radius.
Yes, it's a radius. Half of the diameter it is. It is radius. So this is a radius. Okay. Now, this one is a radius. Yeah, radius. Okay. Here, north, south. And what shape is the magnet? The shape of the magnet also can be the one of the answer here. The shape of the magnet over here, we call it as, okay, we can say this, curved magnet. Simple one is curved magnet. Curved magnet, or you can write radial magnet. The shape you must know, eh? Curved magnet, or concave magnet, or radial magnet. Okay, curved magnet, concave magnet, or radial magnet. Okay, so if it's a curved magnet, what happens here? If it's a flat magnet, this one is a, this is a flat magnet. So flat magnet, it will produce a magnetic field that curve outward. But here, the magnetic field will be a curve inward. It is not goes outward. Yeah, it will be curved inward. Drawing like this also they can give you, but they will give the shape of the magnet. Then you have to complete. Or maybe they'll ask you to draw the correct shape of the magnet, and also they ask you to draw the magnetic field. So make sure that is curved inward. And don't forget to draw the direction of the magnetic field. Draw this. Okay. Why we have to choose a curved magnet? Why? Okay, the reason to concentrate magnetic field, or to concentrate magnetic flux. The lines, the field lines, we call it as flux, F-L-U-X. Okay, or you don't want this to concentrate the magnetic field. You don't want this, you can write, okay, that's now, okay, actually there's one more that we can place in between. The one I will, no, after this I'll give you one more. Yeah, so you take this to produce radial magnetic field. To produce radial, yeah, R-A-D-I-A-L, radial. Okay, to produce radial magnetic field. So if PM said untuk menghasilkan medan magnet jejarian, yeah, to produce radial magnetic field. So the condition is not suitable. There, don't choose. Okay, they will ask a few times in the exam. Don't choose a flat magnet. It's not suitable. So we have to choose curved magnet. Okay. So now, if let's say in between, this is a front view, front view. Okay. So wait. This is a curved magnet. curved magnet. And then if you place a soft iron core, if you place soft iron core in between, soft iron core. Okay, if you place a soft iron core. It's a soft iron core. All this they won't teach in school. So I try to teach you a bit detail. So if you place a soft iron core in between the magnetic field of the permanent magnet, okay, into the permanent magnet, let's say here north or here south, what happened? Okay, look at this. This is what we call radius, right? Radius. Radius, yeah? Radius. So that's why we say radial magnetic field. So what happened is the magnetic field, so here it is. Okay, so it produces what? It produces radial magnetic field. Radial, okay, radial magnetic field. So this is the correct answer. If you place soft iron core, but without soft iron core, it will be like this. And don't means the arrow. Okay, don't miss the arrow. Okay, so it will produce a radial magnetic field. See, very long story. We discussed already 2 experiments. We draw the catapult field. This also catapult field. Catapult field which will produce a turning effect. But there will be a pair of forces acting. So here it's involved diagram, which also can be the answer in the exam. Okay. So still got a direct current motor. That one take at least 45 minutes. But anyway, here most of it already complete. Only need to go through how the turning effect finish, correct? So we need to go through how the DC motor works and what are the factors that affect the speed of the motor. So the factors we'll discuss, experiment we'll discuss now. So over there, I'm not going to discuss the experiment. Okay, I'm not going to discuss the experiment. Finish it. So I think next class, less than 1 hour, I can finish on this subtopic. Then we are going to discuss questions. For time, we'll start with the subtopic number 3, electromagnetic induction. Okay, so today I want to stop over here because of this. I got another class. Okay, those who want to join the Saturday class after this, yeah, the class will be 9 to 11. Yeah, previously I said 10 to 12, so I'll change to 9 to 11. Make it in the morning. Okay, thank you very much. See you on next week. So make sure that you print out. Yeah, you print out the DC motor, and also I will give you generators. Please print out, don't reduce size, make it bigger because you're going to label. While I'm explaining over here, you're going to label. Important is labeling and identifying something over there. Okay, so that's all. Thank you very much. See you next week.
Thank you, sir.
Thank you, sir.
Thank
you, sir.
Welcome, sir.
Thank you, sir.
Welcome.